Good afternoon. Thank you for attending my presentation. My name is Roberto Porcu, and today I'm going to talk about mfix-hexa. mfix-hexa is a computational tool that my group and I are developing, and is for simulating multi-phase computational fluid dynamics. And actually, the goal of the project is to develop a tool for contributing in the development of novel technology for producing electrical energy in a more green and environmentally sustainable way. And also during my talk, I will discuss about a hybrid particle-in-cell discrete element method approach that I'm implementing in mfix-hexa. So why do we want to investigate novel ways of producing electrical energy in a more green and environmentally sustainable way? Because standing to some data analysis coming from the source, for example, is in this case is the United States Environmental Protection Agency. For example, in 2016, and nowadays probably this estimation is the same, one of the major sources of CO2 production comes from electricity generation. And CO2, as you may know, is one of the greenhouse gases that are in our atmosphere. And the more we artificially produce, the more the greenhouse effect increases, and the more we have like global warming and climate change. And actually, carbon dioxide composes almost a very big percentage of all the greenhouse gases in the atmosphere. So, okay, so electricity generation is one of the major sources. But how do we actually produce electrical power? Well, in the US, more than the 70% of all the electricity generated comes from burning fossil fuels, and this happens in thermal power stations. And the problem is that when we burn fossil fuels, we have the combustion generates some gases that goes in the atmosphere. We can filter them, but trying to capture CO2 is hard because it's mixed to other gases that are produced by the combustion. So it's not easy to capture CO2 in the standard way of electricity production in thermal power stations. So is there a way in which we can actually try to solve this problem, like separate CO2 from the other gases before we emit in the atmosphere? And the answer is yes. The answer actually is represented by chemical looping combustion. In chemical looping combustion, that is represented by this diagram, what happens is that the oxygen that is needed for the combustion of the fossil fuel is not brought by air, directly by air, as happens in normal processes, but it's brought by a metal oxide. The metal in general is copper or nickel. And what happens is that the metal is oxided in the air reactor, and it gets oxygen that carries oxygen in the fuel reactor. Here, a reduction takes the oxygen back from the metal, and the metal is brought back to the air reactor. In this way, what we have is that from the fuel reactor, we have a stream coming out that is made only of water vapor and carbon dioxide. And in this way, it's much easier to capture carbon dioxide at the end of the combustion. So we actually have laboratory scale chemical looping reactors. One example is in Morgantown, West Virginia. We have in the National Energy Technology Laboratory. And we are doing experiments. I mean, not us, but our collaborators are doing experiments with that. It's working pretty well. So why are we not already producing it, producing electricity from a chemical looping reactor in industrial scale? The problem is that if we want to build the industrial scale chemical looping reactor, what happens is that actually it doesn't work as expected. So at the moment, we cannot do industrial scale production of electricity with chemical looping reactors. So, so this is the reason that motivates the adoption of numerical simulations, because we want to understand why you know, why it works pretty well for laboratory scale, but if we scale up to industrial scale, it doesn't work anymore. And only numerical simulations, of course, can give us insight in the physics of the problem, what is going on in point by point, okay? And so, and actually, this is a more detailed scheme of a chemical looping reactor. And we actually already have software for simulating chemical looping reactor. MFIX is a code that was developed over the past 30 years, is working very well, and was developed specifically for solving problems of reacting multi-phase systems. And, okay, sorry, the video also is showing that actually, yeah, we're already simulating chemical looping reactors, okay? So we have it, right? We should be able to design the industrial scale chemical looping reactors. Well, the answer is not yet, because the problem that we have right now with MFIX is that we need to simulate, in order to simulate industrial scale reactors, what we have to simulate is like around 100 billion particles that our goal is to have a simulation of more or less 5 minutes in real time and with a, let's say, a simulation time of 2 days at most. And this is, of course, extremely computationally expensive, and it's a challenge. And MFIX right now is not able to solve such a, to perform in this way. So this is how MFIX-Hexa was born, to solve this problem, in the sense that we want to couple the potentialities of MFIX with the potentialities of AMREX. So like being able to run our code on modern supercomputers, and also make our code ready to run on the next generation exascale supercomputers. And, but, okay, so, and we're actually, this is also the first part of my work here in the lab. I was working on parallelizing MFIX for making it ready to run on GPUs and hybrid MPI GPU environments. But is this enough? Like, so once we already have our code on GPU, but is this enough for what we want to do? So simulate like 100 billion particles? Well, the answer is probably not, because what happens is that right now we are using a model, we are modeling particles in a very accurate way. We keep trace of interaction, particle by particle interaction, so all collisions, and with interaction with walls and everything. But the bottleneck is actually particle-particle interaction, especially in the fluidized beds, because here we have a very high volume, solid volume fraction. And as you can imagine, if we have billions of particles that we have to understand how they interact with each other, is extremely expensive computationally. So indeed, right now we are, MFIX-Hexa implements a discrete element method for modeling the particles. This method is very accurate, but is very expensive. And what we have, for each particle we take into account we keep trace of a neighborhood. So all the neighbor particles, whose center is within a certain distance from the center of this particle that we are considering. And a collision happens when two particles overlap. And so actually, what happens is that the forces that act on the particle are the gravity, the gradient of the fluid pressure, drag, so interaction with the fluid, the interactions of the particle with wall, and also particle-particle interaction, so with the interaction with the other particles in the neighbor, okay? And this is actually the bottleneck, because as you can expect, like we have every time, every update, we have to compute all the interaction with all the neighbor particles. And how do we compute the interaction? So we have a normal and tangential component of the force that act on this particle. And for the normal component, we are taking into account a linear spring dashpot model that is described by this diagram. And for the tangential force, we are using a Capesilatro and Desjardins model. And this is actually some simple example of how it works. This is an interaction with the wall. We have a perfectly elastic interaction. And this is an example of collision between two particles. So, okay, so this is very accurate, and we want to, like, we want a code that is actually accurate, of course, but the question is, do we really need to be that accurate in a fluidized bed? So when we have so many particles all together, do we really need them to be so accurate? And our guess is that no, we don't need to be that accurate in a fluidized bed. And for this reason, we are taking into account the particle in cell approach. Particle in cell approach is less accurate than the discrete element method, but is much faster. And this, in this method, what we have is that particles are grouped into parcels, and we don't need to compute parcel interactions. So why? Because in this case, the linear continuum, the equation of linear momentum conservation is more or less the same as before, but what the biggest difference is that now we don't have any more collisions between particles, but we have another force that replaces that kind of collision, in the sense that this force is proportional to the opposite of the gradient of this interparticle stress that we compute as function of the solid volume fraction. Okay, so what happens is that if we have a region where the solid volume fraction is very high with respect to the neighbor regions, what happens is that we will have a gradient, a force represented by the gradient of this stress. And that force will move the parcels from the region where we have a higher solid volume fraction to the region where the particle volume fraction is lower. And this model is the Snyder interparticle stress model. And okay, so, oops, sorry. So, but like, okay, now we have one model, the discrete element method, which is very accurate but expensive, and this other model that is not that accurate but much faster. How? But you know, in our chemical looping reactor, we don't have just fluidized bed. We have other regions where we need to be accurate. We need the code to perform, you know, to simulate the phenomenon in an accurate way. So the idea then is to divide the problem to use this approach, this hybrid approach. So we want to use the discrete element method in a more dilute region where we need to be accurate, and the particle in cell approach in the fluidized bed where we don't want to be that accurate, but we want to be fast. The problem is the intermediate region, the transient part between one and the other, because here we have to decide how to model the interaction between particle and parcel, okay? In particular, if after the interaction they move, for example, up to the discrete element middle region, or they move down to the particle in cell region. So in the first case, if they go in the discrete element part, we have to break the parcel into all the particles that compose it and treat them in a discrete element method way. And conversely, if they go down to the particle in cell, we have to maybe we have to include the particle in the parcel and treat everything as a parcel. So this is something I still have to investigate. I just finished to implement the particle in cell that we still need a bit of testing. So this is something I'm working on. Okay, finally, I would like to show some results that we have about the performance of our code right now. So for a prototypical CLR on one summit node using the discrete element method, what we have right now is that if we take into account as reference a simulation with 36 MPI tasks, right now with load balancing, we can reach 54 speed up with knapsack load balancing. And you can see that the cost per time step is pretty constant. So this speed up is constant time step by time step. This is the reference simulation, and this one is the best performing one. And this is one result that actually Oscar helped me to obtain to visualize. Actually, it's one simulation that he did, and we tried to make the best way possible to show that, like, for example, here you can see that you have like a bubble of gas that is coming up and is making all the particles rise. And finally, I would like to thank all my collaborators here in the Berkeley lab, and Oscar, John, Johannes, Andrew, and Michele, and our other collaborators in the National Energy Technology Laboratory, William, Mark, Jordan, and Madhava, and also our collaborators at the University of Colorado Boulder. And thank you. And question?
So the equation you showed was a balance of linear momentum of the particles.
Yeah.
But is there like a plan to capture like the hydrodynamic interactions as well, or is that not involved?
You mean the interaction with the fluid? Yeah, of course. It's in the other components of the force. So, for example, here you have the drag is actually the interaction, the solid-fluid interaction. And you also have the gradient of the fluid pressure that is also acting on the particles. So you take into account these both for the discrete element method and for the particle itself.
But you don't, right now, you don't care about what the fluid is actually doing.
So yeah, right now what we are doing is that we update, firstly we update the fluid phase, and then we keep the fluid like frozen, and we update the particles in one simulation step. So yeah, right. But we are Michele is I think was I mean, we have in plan to work on a novel algorithm that is that is actually going to improve this in the sense of making it more simultaneous, like to have to compute more or less at the same time both to update at the same time both fluid and particle phase. So yeah, that's something in the future.
So, comment one is, I think you win the most absurd captions prize.
Sorry?
The captions. Text.
Oh.
From Roberto Cuckoo to Taco John to beheading somebody. Okay, but there's actually a serious question. So, what, you may have said this and I get distracted by that. What are the most important guiding principles in this transition region? Do you have a physical feel for that? You know, like, we want to conserve momentum, right? That's obviously important.
Yeah.
What, I mean, we're changing from one representation to another one. It's obviously an approximation. Do you have a sense of what's the most important? Like, conservation of momentum is obviously important.
Yeah, definitely, yes.
What else? Do you have a feel for it? Or is it just kind of come out in the math? So if I understand correctly, in the PIC, you still have the same particles. This is different from the coarse grain, right? You still have your same particles. It's all about the interparticle force?
It's about, yes, it's about how that now you don't compute the interparticle force, you just update, not taking into account collisions, you just consider this solid pressure that moves particles to regions where they are more dilute.
And is your concept that in the intermediate regions, some particles will collide individually and some will feel the stress?
Yeah, that's a good indeed, it's an important point.
Yeah.
Yeah, I have to think about it. I don't know now how to answer that question. Yeah.
So you do two things when you switch to DEM. When you switch from DEM to peak, you gathered like the particle with parcels, and you stopped computing the interaction one by one, or like by pairs. Which of the two is more expensive of the work you did? Like if you did not group the particle with parcels, is that expensive, or is that a lot of? Okay, let me rephrase that. What's more expensive between having more particle or being able to do pairwise interactions? What's the most expensive of?
Well, I think that computing collisions is much more expensive. In the peak, you pack the particles in a parcel, but I think that's like it's not something that you do every time.
Yeah. So you could keep a single particle in a parcel, just not compute the interaction, and that would make your transition much easier.
Yes. That could be, yes.
So you still have a lot of particle in the peak section, but somehow transitioning from one to the other
is much easier, right? Yeah.
Okay.
Yeah, that could be a solution. Still, yes, you still have to understand how to write, like, one for DM, you have to compute a collision with the other one. You don't, actually it's not colliding, it's just updated on the basis of the stress, the solid stress. So, yeah, I still have to think how to still preserve momentum.
Yeah.
But thanks for the.
Thank you.
Thank you.